I think what we're all here for is actually what we derive from the data, right? I think at the end of the day, as the various panelists and the presentations that have been done during the day, everyone wants to talk about business value. So while there's a lot of energy being spent on big data, it's actually all in the name of deriving value. And data is just a means to an end. It's really the knowledge that we're after. Today, what we have is, in the industry, a lot of concentration around being able to query data, being able to query ever larger amounts of data, being able to query data faster. But at the end of the day, it's fundamentally the same approach that we've been using. It's still query-based. And at the rate at which data is growing, this approach won't scale. We believe that in the future, we need to be able to address this problem differently. We need to be able to derive automatic answers from data. We need to be able to enlist machines to analyze data, more so than the manual methods that we do today. As a result, one of the things that was brought up in the panel before me was that we'll be able to make accessible data analysis to people that don't have degrees in statistics and mathematics and computer science. And that, I think, will be the true revolution of big data. I think everyone would agree that data can solve some pretty expensive problems. These are all verticals that people in this room are familiar with. And just to give you an idea for the sense of the problem, of the business problem, all of these industries, these are customers that we work with at my company, all of these industries are generating data at a prodigious rate. Drug discovery today is a data problem. To develop a single drug takes $1 billion and about 500 people working over 10 years, and then maybe they have a 10% chance of success. This is not due to a lack of data. They have a lot of data on what would make that process more successful. The gap is in the analysis of that data. Similar story with oil and gas. It takes $250 million today to drill a single oil well. The chance of maybe finding oil in that well, it's about 15%. Now imagine that we could add value to this. Imagine that we could move that 15% to be 50%. Imagine that we could move the drug discovery to be from 10% to maybe 20%. This would have enormous implications for our society. These are all really, really big problems. And they are not suffering for a lack of collection of data. All these industries combined sit on petabytes upon petabytes of data, most of which never gets analyzed precisely because we approach the analysis of the data the same way that we used to 10, 20, 30 years ago. The top of this slide got cut off, but it says in the past 3 decades, the way that we find knowledge from data has not really fundamentally changed. The scale of it has changed. As an industry, we've done really, really well in terms of being able to bring the cost of collecting data as well as the cost of storing that data significantly down. But we still rely on experts to be able to analyze that data. We still rely on formulating questions of that data to find knowledge from within that data. And there's a fundamental limitation here. How many questions can we think up? What about the questions that we never asked from that data that might yet reveal something of value? And as long as we stick to this model, we're bound to 2 limitations. One is our ability to ask interesting questions. The second is the need for expertise. These 3 approaches, whether it's databases, BI tools that were discussed earlier, or even more sophisticated techniques such as developing mathematical models, all require significant expertise in being able to understand how to interact with the data. In particular, the BI tools, they're meant for a different class of user. They're meant for users who make everyday business decisions, but are not expert users in data analysis. So how, as an industry, do we bring our expertise to develop solutions to make it more accessible for these folks to do complicated discovery in data without having deep knowledge about data analysis techniques? This requirement for manual analysis of the data is a significant bottleneck. The rate at which we can produce data and the rate at which we can analyze data are fundamentally different by orders of magnitude. And as a result, less than 1% of the data that we have today is ever analyzed. We've talked to a number of customers that have collected data that's 10, 15, 20 years old, very expensive data sets that took many man-months to collect, that never get touched simply because of a lack of scale, a lack of ability to do something more intelligent than manually query that data. And this gap continues to increase. Data is expected to double every 2 years for the foreseeable future. Our computing power will continue to double roughly in that proportion as well. However, our ability to derive value from that data is not following the same curve. As an industry, collecting data today is cheaper than ever. We have sensors that are very cheap. We have logs that are cheap to generate. We have smartphones that generate data all the time. We have pictures that we can snap anywhere. We have brought the cost of collecting data down significantly. We can also very efficiently store that data. The gentleman on the panel before said it previously used to cost $500,000 of a very expensive SAN device to hold data. And today, you can buy a farm of very cheap SATA drives and host as much data as you want. In fact, Amazon has very publicly put up numbers that suggest how cheap it is to actually be able to store data. And Amazon Glacier, at I believe it's a cent a gigabyte a month or something like that, gives you an idea of how cheap it has really become to actually store data. But our ability to analyze that data is very, very limited. The complexity of data is growing. We have customers that used to collect sensor data. Maybe they'd collect a couple of hundred sensors per machine they were tracking. They would throw away 90% of that data. They would track 20 sensors because that was all they could analyze. So over time, what's ended up happening is because of our limitation to ask questions of data, because of the various sources of data, because of the volume of data, our tools to derive actual value from that data have not kept up. And I think that's really where we need some fundamental rethinking in how we approach this problem. That's the subject of my talk today. So to take a step back, I'm going to talk about something that at face value might sound a bit esoteric. I'm going to talk about topology. And topology is a very old branch of mathematics. It's 300 years old, and it's primarily concerned with the description of shapes of different things. But more recently, in the last decade, there's been this idea of data itself having shape. Point clouds of data, or data samples, can be thought of as points in a multidimensional space, and that space has shape. And what if we could apply techniques, well-known techniques from a very well-studied branch of mathematics to data? Would we learn anything new? And the answer to that question is a very resounding yes. You can see the quote below from the folks at DARPA who funded this research at Stanford. And they consider this to be one of the biggest advances they've seen in over a decade on data analysis. The research at Stanford was done by Professor Gunnar Carlson and some of his associates. And Professor Carlson is still at Stanford, but also works very closely with our company. And his idea was, can we take these topological techniques, apply them to data, and actually learn something new? And they demonstrated within the scope of their research that, in fact, they could learn not just something new, a lot of new things. And so the company that I work for, ISD, was born out of this concept of commercializing this idea of topological data analysis. There's a couple of very interesting things about topological data analysis, and I won't go too deeply into the math, but stick with me because these are things that are pretty fundamentally different from how we approach data analysis today. There's this notion of coordinate freeness. The way to think about this is typically when I'm looking at any data, I'm approaching it from a frame of reference. I'm approaching it implicitly or explicitly from a certain bias. And if you could remove that bias, then you might discover features in that data that you hadn't thought to look at before. So this notion of coordinate freeness, the entire mechanism of topological analysis only depends on similarity of data points, not what frame of reference you're actually looking at them from. And this becomes very important, as I'll show in a couple of the use cases in the slides ahead. The other property is invariance to stretching and pulling. Deformation is a nice term, but it's this basic idea that I could take a shape and I could maybe twist it or maybe pull it, maybe stretch it, and it still looks the same. And I use the word looks very deliberately. This is a very visual metaphor. The human eye is very good at recognizing that the letter A above and the letter A below are both letter A's. We're very good at throwing out the noise in the data, just physiologically very good at throwing out the noise in the data. So maybe we could use that technique on actual data and see if we can build more noise-tolerant techniques to analyzing data. The third property is this idea of compressed representation. All the data problems that we've talked about today involve really big numbers, petabytes, terabytes, billions of rows. It is beyond the capability of any human being to be able to visualize the entirety of such a data set. We need a way to, if we are to derive insight from that data, we need a way to be able to represent it more compactly. A very trivial example given here is that a circle actually would require a lot of description if you were to simply describe it point by point by point. However, if you were to describe it as shown here, there's other ways to describe a circle that are much more compact, you actually get a very compressed representation of the data. And this also turns out to be a very interesting property of topological data analysis. To give you somewhat of a more visual example of this, if you look at the two plots at the top row, assume that we had age, weight, and height, and they were uniformly distributed. And I'm using 3 dimensions here because as humans we can actually perceive and visualize 3 dimensions. What you would see is basically a bunch of noise. You would see a projection of dots on a screen and they would really have no pattern to them. But in reality, age, weight, and height are correlated. And what that correlation actually means in 3 dimensions is shape. If you noticed when that box was spinning, there was a very distinct curved shape that was spinning. And the entire premise behind Professor Carlson's research was that that shape has meaning. We happen to know that age, weight, and height are correlated, but if you didn't know that, that shape would tell you that there's something correlated about those three numbers. Similarly, you can think of more complicated shapes, clusters, maybe flares that sort of overlap each other in three-dimensional space, maybe even loops. And you can see the projections of those below and how they change depending on what perspective you look at it. Now, this is a very stripped down example in 3 dimensions just to make it accessible for people to see. But imagine for a second that your data has 1 million dimensions. We actually have customers whose data has 1 million dimensions. We can do this in 1 million dimensions. And one interesting thing to note about this is the projections that are displayed at the bottom are typically what people think of as machine learning today. They project their data in a certain way. And you'll notice that depending on which way you're looking at it, you might see something, you might not see something. And the techniques that we use today are exactly that. They're hit and miss. You might see something, you might not see something. And that's where we think that topological data analysis can actually bring a completely new way of looking at data analysis. There's a couple of other nice properties of TDA, and I'll just use the acronym from now on because it's long to say topological data analysis. There's a couple of nice properties about TDA. Having geometric representation of data suddenly becomes a common currency for talking about different machine learning methods. There's a lot of folks today who talked about using, clustering techniques for recommendation or specific other machine learning techniques, PCA, SVD, what have you, for different use cases. But they're all point use case driven. And I think the consensus in the room was that those techniques are constantly evolving, and there's no one machine learning technique that is right for all the problems. The beauty of topological analysis is that it gives you a language in which you can talk about all kinds of different machine learning techniques. In fact, on our platform, we use hundreds of machine learning techniques concurrently to get different perspectives of the data. The network structure that's generated as a result of this analysis has an interesting property of its own. Networks are easy for the human eye to make sense of. We can visualize billions of points on a single screen, and the human eye is very good at picking out features in that shape that you can then go and understand deeper. But it's a network structure at the end of the day. We can programmatically query that structure for features that are interesting in that data. It's not a technique that's limited. It's a very general approach to data. It can handle different types of data. It can handle numeric, text. In fact, it's agnostic to the type of data that you're talking about. For these reasons, we believe that TDA is actually not just a very powerful technique, but a fundamentally transformative technique in the way that we're going to approach data analysis in the future. It enables us to enlist the help of machines to do discovery that to date has been very manual. I'm going to walk you through a couple of examples, I guess more use cases from customers that we've seen. There's going to be some diagrams on these pages, so before I jump into that, I sort of want to orient everyone a little bit. Topological analysis generates a network structure, but the network structure is slightly different from what you would think of as a Facebook social graph. The nodes on this structure are actually collections of data points. And two nodes share an edge if those collections have any elements in common. It's not really necessary to remember all of this, but it does give you a sense for how to interpret the graph. If there are any questions after the session, I'm happy to help answer sort of specifics. This is again, I apologize, but the title seems to have been cut off. This is an example from, if anyone here is familiar with data in the life sciences, there's been a project called the Cancer Genome Atlas, which basically tracks different types of cancer and has a large repository of data on patients, genetic data about those patients, mutation data about those patients. In this particular data set, we were looking at 500 patients and roughly about 30,000 genes and point mutation attributes across those patients. Now, to give you a sense for how this works at a pharmaceutical company who's looking at this data, they look at 30,000 dimensions. Essentially, that's what those genes are per patient. There's 30,000 dimensions of data. And they typically select a very small number. And they try to build models off of that small number. And they maybe build a model, they decide that it's not the best model, maybe it doesn't work so well, they throw it away, and they restart. That entire episode, sort of constructing a model, maybe using it, maybe not, is an effort of many, many months. It's typically based off of very expensive data and very highly paid data analysts. This map here was generated in a few minutes. So you can see right here that the techniques accelerate the process of discovery of model generation by orders of magnitude. Different use cases are targeted for this type of a data set. You could stratify patients. You could identify biomarkers for certain types of diseases. You could target treatments for patients that might be more receptive to a specific kind of drug. If you're a drug company today, you are likely already using this data, and some of our customers are. And you can do interesting things with this type of a network. You can find segments of patients that have specific gene mutations. And within that segment of patients, you could say, hey, maybe I should see which of those patients are also part of a specific treatment group. If I have a drug that addresses a particular part of this network, now I have a way of delivering treatment to a patient in real time when a patient comes in to say, where do they belong on this map? What treatments were effective for that patient? And target very personalized treatment to every patient that comes in. And this is beginning to happen today. It's not just cancer data. There's clinical data, electronic health records, genomic data, translational medicine. The life sciences world in particular is awash in data, as I mentioned. And there's a way for us to be able to greatly speed up the analysis of all of that data. This network here was constructed off of a much larger set than the previous one we saw, much higher dimensionality, but still the analysis does not get any more complicated because the data is more complicated. And I think that's the takeaway from all this. As I mentioned, these techniques are completely general. As a company, we work across a number of verticals, and we have customers that, the top here says machine and sensor data, by the way. We have customers that work with sensor signals across many hundreds of thousands of machines. And as I mentioned before, today the paradigm is we collect X amount of data, we typically use 1/10 of it, maybe 5% of it. And it's not for a lack of will to use that data. It's simply because they don't have the techniques and the manpower to be able to deal with it. What we believe is, as a result of that, a lot of the models that are being built on this data are not as optimized as they could be. If you're flying an aircraft engine today, and they have a model on predictive failure of that aircraft engine that's being built with 5% of the sensors they track, that model is likely going to be a whole lot better when you get to the long tail of those factors and are able to build a comprehensive model across all the factors that they track. And this is really one thing that's now possible with this technology. Similarly, oil production data. I talked about this earlier. It's extremely expensive to be able to drill oil wells. The probability of success is pretty low. However, they track a lot of things. They track soil quality, sediment information, the pressure on the drill bit, the types of rocks that they're hitting, the amount of moisture. They track a lot of stuff around that particular project. However, most of it is just simply collected, stored, to be analyzed at a future date. And what we enable them to do is actually optimize that process significantly. Now, we're able to talk to customers and say that in near real time, we can get them data about that drilling project as it's happening. And that literally is a game changer for some of these companies. We have a couple of customers in the security side of the world. The top of this slide says malware data. The gentleman from Symantec was here earlier talking about how the world no longer relies on just pure signatures of malware because that's no longer a good enough indicator. This data here was generated off of 1 million log file sequences, basically tracking system call activity for applications. And the system automatically stratifies what appears to be suspicious programs. None of these graphs that I showed here were constructed with any kind of query. No one sat at a computer and said, tell me what looks suspicious. They simply inputted the data and allowed the system itself to discover these patterns in the data. And that's the fundamental change that I'm talking about. As I mentioned, it's not a technique that's specific to any data type. This is a map of all of Apple's patents. If you have any friends who are patent attorneys, or maybe there are some in the room, you understand how the process of discovery on patents happens. You sit at Google Patents and you sort of type in some keywords and you see a giant list and you sort of one by one just kind of walk down that list. Well, imagine if you had a picture, right? All of these are clustered automatically by the type of the patent. And this is very key because patent disclosures typically have different type of language. They're very legalese. Some of the language is obscured. But if you can see, the fonts are a little bit small and kind of hard to read here. But there's clusters in here. Like this is patents related to camera stuff, right? And this is patent related to display technologies that they have. And you can immediately see how this would be valuable, not just to Apple, of course, but to potential customers, potential litigators, where if I'm looking as a company about where to place my bets, or where there's a gap, or where potentially there's an overlap with somebody, I now have a way of doing this that is so much more efficient than what I was doing yesterday by crawling Google results. The last case I'll talk about is this idea of validating models. We've come across a number of customers and we've sort of asked them and said, well, how do you develop your models today? How do you decide whether something's working or not? And a lot of the times, it's pretty surprising, but models are trusted. They generate a model, they validate it against some small set of historical data, they put it into production, and then typically there's an inbuilt implicit trust that the model is doing the right thing. This model here was generated from emergency room data. And here on the left side are the predicted results of the model. And I won't go into details of the graph. If you're interested, you can sort of come find me after the session. But the blue on the graph was the predicted survivors. And the red were the predicted non-survivors. And you can see the model did a pretty good job of predicting the non-survivors. Not so good at predicting the survivors. And not so good by a mile, right? And this whole idea of model verification is just as expensive as model creation. And so typically there's a big lag in the time that a model is deployed to the time that somebody goes around to check it and say, hey, did that model do the right thing? There's a big lag, and there's tremendous consequences for that lag. And so we aim to fill that space with the technology that we have. So I'll leave it there. I hope I gave you a good sense for the techniques that we're proposing. Topological data analysis, I believe, is a fundamentally transformative technique. Our company has commercialized that technology. We have, in production with a number of customers, demonstrated the efficacy of this technology. And I think as an industry, it's time for us to take a different approach. Rather than the old mechanism of manually querying and modeling data, it's time for us to take a different approach that really will enable us to actually get to all of the data that we're collecting. Thank you.
And obviously, if you had more time, we would have covered applications in cosmology, all the protein folding stuff.
Yes.
And I was on the board of a drug discovery company, which was in silico.
Yep.
In the in silico, this is amazing value.
Yep.
And now we have time for questions. Okay.
Hi, my name is Dheeraj. So the question I have is that the slide that you showed where you were showing the log data and how you were detecting malware from the log data. Can you tell me a little bit more about how exactly are you detecting that what is malware? Because you also mentioned that you don't have to know upfront what type of data it is. So when you're looking at, let's say, a log line, you just know, you really don't have that much information about what is being logged in that log line, yet you are able to derive that, okay, this is a malware. So can you tell me what are these nodes, what are the links between those nodes, and how do you judge that this is malware?
Yeah, I can give you sort of the short version of it, and then I think maybe if you don't mind, we can catch up after the session as well. So the way to think of it is that all of these nodes on the graph represent collections of very similar log data, right? And you can think of log data as being just different points in a log that collect at different timestamps, collect different activity. All of these points happen to come from specific programs at different times, and the system is able to classify which ones are similar to each other, right? And there's a bit of a nuance here in the sense that up here there's a yellow-colored group, and down here there's a yellow-colored group. And this yellow-colored group is actually malware. This yellow-colored group is actually not malware, but looks very significantly like malware, right? And you'll notice that on the analysis, they're very separate, right? And this would have been a false positive in other techniques, right? Where you would have classified this as malware. Whereas with this technique, because of the nature of how topological analysis works, you're actually able to detect certain features that other techniques are not so good at detecting. And you're able to classify this better. I can go into the actual implementation details, maybe offline, in terms of what the actual log outputs were and sort of, what they map to on there. And I'm happy to do that after the session.
Hey, hi, I'm Raghav. It was a really good perspective to see this. Can you quickly go to the last slide where you showed the patients who survived and not survived?
Yes.
So the question is this. You said the way the topology-based modeling which you are doing, two advantages you said. One, is it faster? And it's easier to validate. These are the two things you said, right? Taking this example, if you see the model is predicting, how do you explain that your model is faster? I couldn't get connection.
Sorry. So that's a good question. Let me clarify a little bit. So in this particular case, the two graphs that I'm showing here, these are not our models, right? So we have a model for this. This is not shown on this slide, but these are not our models. This was a customer that we were working with who had this model here in place. Then they went back and they actually looked at sort of the results they're getting from that model. Their issue was how do we improve on that model to get what we were actually looking for, right? And the thing to keep in mind here is that this data, I don't think it's shown on this slide, but this data has, I think, a few hundred dimensions to it. So for them to go back, they would have to go through individually each of the factors, essentially just recreate a model and just test it, right? That's really the only way for them to go about this problem. Whereas what we're arguing is that if you have a holistic view of the data, right, you can actually target, right? I don't have a live demo here, unfortunately, but I can select any arbitrary group on this graph, and I can dive into the factors that make that group unique, right? And I can then iteratively I can iteratively inform my model rather than going back recreating the entire model from scratch. So that's what we're arguing for. Sorry, you had a question?
And I wonder what if there's a concept of outlier in this topology approach, and could you comment a little bit about that?
I guess I'm not sure how to interpret the question. So there are outliers in all data. However, I mean, just to use this graph because it's up on the screen right now as an example, this group here could be construed as an outlier, right? Because it's reasonably far enough away from the central mass of that graph, right? But topology itself is actually very good at identifying but yet including outliers. So we don't require you to throw away outliers. We don't require you to a priori go and identify something that doesn't fit and throw it out of your analysis. We actually include all of it in the analysis. But it shows up on your graph. You're easily able to identify sort of which points may be further away from the group. And I think in some of these cases, they may actually be completely disconnected from the rest of the group, right? But we actually probably should not be throwing away the outliers because a lot of them actually have meaningful things to say about the data. So we don't a priori do any filtering of the data that throws away any outliers. I hope that answered your question.
Yes, it does. So if you go back to your patent example, if I use your structure and do a patent search on a particular invention disclosure and patent filing, would it be a complete search?
Complete in what sense?
Complete in the sense that all the patents that are related to that particular field, particular space is all searched for, is accounted for?
Yes.
Okay, thank you.
And we will be getting ready for the panel. It's an excellent talk, and I have lots of things one can do with this in drug discovery as well as genetic gene expression, cosmology, name it.